Dr. Willis?
Yes, Francisco. Can you hear me?
Yes, I can hear you.
Okay. So should I introduce Paul?
Yes, please.
Thank you very much. So thanks, Francisco and everyone. And it's now my pleasure to introduce Dr. Paul Fallon, who is going to give us this seminar today. Dr. Fallon is a semi-retired scientist who has spent the past 6 years focusing on astrophysics research. He began his scientific career as a research scientist at De Beers Industrial Diamonds after completing his PhD at the University of Cambridge in electron microscopy and electron energy loss spectroscopy. After a successful career in management, consulting, and banking, he returned to astrophysics, where he has collaborated with Prof. Deck Smith on research into astrophysical measures, including maser flaring and polarization studies, resulting in several publications. Thank you very much, Paul, for accepting to give us this seminar, and you are welcome.
Thank you. Thank you for the opportunity to present this work. So this is all based on a paper that myself and Dirk presented recently, or published recently. It was published just over a month ago, and it's on polarization. It's of a sample of methanol masers, and it's all observations at 6.7 gigahertz. So I'll talk a bit about what we have in the paper, and then also some of the things we've come up actually challenges or contradicts some of the existing views that people have, and I'll speak a little bit about that. Just show you sometimes that information that has been published previously isn't always correct. It's a fairly short, high-level presentation, so please stop me if there are any questions or if you want me to speak louder or if there's any misunderstanding. And also, sorry, let me go here. Can everyone see my cursor? My hand?
Yes.
Yes, we can see it.
Okay, so at least you can point with that. Okay, so the basis of the study, there was the Greenbank telescope sent out a special proposal call, and that was sometime late 2022, so almost 4 years ago. And they said they had a lot of free capacity to look at our angles that were away from the galactic center. So myself and Dirk submitted a proposal. The idea behind the proposal was to look at 21 different star-forming regions. We were going to look at it in full Stokes mode, the idea of getting the polarization results, not just the total intensity. And we were looking at excited OH masers. That's a couple of them at 4.7 gigahertz and at 6 gigahertz, and then also the 6.7 gigahertz methanol maser. We were very fortunate. The proposal was approved, and we got 84 hours of observing time, and we did these observations effectively starting about 3 years ago and finishing early 2024. So relatively recent observations. We initially put a paper together with all of our results, but it was there's a lot of data in here, so we split it into 2 papers. The one I'm talking about today, which is on the methanol masers, and it was published just over 3 weeks ago. And a second paper looking at the excited OH masers. We've just finished that paper, and it was submitted about 3 weeks ago, so we haven't heard yet back from the reviewers. On the right, this diagram I've got here is something that most people should recognize. So this is just of a protostar. So sitting in the center here is a protostar. And then what's fairly well known is you get these sort of strong jets, or in some cases just general outflow coming out from the protostar. But then rotating around the protostar is this accretion disk, and the material falls onto the accretion disk. And this is how the protostar slowly grows to form a fully sort of functioning star as we know it. What is generally assumed or generally believed is that in the accretion disk, you have, in particular, the 6.7 gigahertz methanol maser. Whenever you see these methanol masers, you know you're looking at a high mass star forming region. The view is that the methanol masers sit in the disk. There is some view that they might sit just slightly above or below the disk. You also in the disk or the outer regions of the disk further out than methanol get the hydroxyl or OH masers. And so that's what our study is about. There are also water masers, H2O, and they sit on the outer regions of the outflow. So that's a generic picture of star-forming regions and rough where the masers sit. It's generally believed they sit in the accretion disk, though it's not conclusively proved. Just some perceptions, and this sort of the basis and something I'll challenge during the course of this presentation. This comes from a presentation as a presentation paper by Flemings in 2010. They did Merlin observations of masers in Cepheus A, which is a star-forming region. And based on their results, their views, the polarization of these masers is all roughly in the same direction. And based on that, they created the schematic diagram, this one on the right, saying if you look at the magnetic fields, they all seem to flow outwards from the accretion disk and seem to flow in the same direction. So this is a view that seems to be somewhat generally held. It was interesting, I was at the European Astronomy Conference last year, and one of the keynote speakers, Boy Lonkar, actually spoke about this and actually sort of gave this schematic as this is what we think is happening in star-forming regions. But I'll come more to this a bit later on. Move down to the next slide. This is the crux of our observations. These observations were done on the Green Bank telescope. So it's a large disk, 100-meter diameter disk. It's a very well engineered and designed instrument. And because it's got a large collecting surface, you end up with a very good signal to noise ratio. So you get some actually great data coming from this. But the other valuable bit of the Green Bank telescope is they have dual feeds. So they have orthogonal X and Y feeds. And because of that, you're able to get the polarized signal. The challenge with having two different feeds is that the signal goes through different electronics for the X and the Y. And in those electronics, you get different gains, so they're not identical. And you also get different phases. Little things like differences in cable length can alter the phase between X and Y. And because of that, you have an issue with the signal you get. So to correct this, there's something called a Muller matrix. It corrects your on-sky Stokes parameters. You correct with the Muller matrix and end up with accurate Stokes parameters. It's quite a process, quite difficult to calculate the Muller matrix, but it's something we did on a project back between 2021 and 2023. So we've got that, we get the results, and then from the Stokes parameters, you are able to calculate the linear and circular polarization. So one of the important values about this result is we do get quite accurate polarization data, and we get very good signal to noise ratio because of this instrument and the calibration. And it's quite important for what we show. I'm going to jump right into what we have, which is just some of our initial results. So we looked at 21 star-forming regions. And of those star-forming regions, and these are known star-forming regions away from the galactic center, about 2/3 of those, in 2/3 of those, we were able to measure or detect methanol masers. Interesting, some of the sources had other masers, excited OH masers, but no methanol masers. So you don't always get methanol masers, but you sometimes get variations of what masers exist, but 2/3 of them had methanol masers. There were about 6 or 7 non-detections. We are fortunate enough, we came up with a new detection, G240. No methanol maser has been seen here before, and I show the spectra here in this graphic. we were able to get 2 observations of G240. We can see that there are 2 profiles here, and both profiles change between the 2 observations, and it shows that the methanol is highly variable, and does probably explain why people haven't seen it before. You see it sometimes, the intensity varies. So we were fortunate enough to see it, and it is a variable maser. Many of the methanol masers are in fact variable. Some are quite very stable, but many of them are variable. Our general results, we did show linear polarization in the range of anything up to about 15%, which is relatively high. And we saw circular polarization up to about a 9% fraction. Interestingly enough, it's only in cases when our detection limits or the polarization ranges were below our detection limits that we didn't see polarization, which I think is quite interesting. So it's only very weak masers where you can't really pick up a 2 or 3% polarization is when we didn't see polarization. So it does hint that many, if not most, of methanol masers appear to be polarized. Just to kind of show you what we end up seeing, sorry, it's quite a complex graphic. It's got 6 panels, and this is of the star-forming region W30H, or its technical name of G133.947. It's a very well-studied star-forming region. These masers have been studied in detail, probably the most studied set of masers, so a lot of data on this. But just to show you an example, most people, or most measurements, or many measurements, only look at the total flux density. So what we see here in panel A. So that's what most people observe. Interesting enough, you see the spectrum here is quite complex. You see many different maser profiles. So there are many maser spots in the region, similar velocities, so you get a lot of overlapping profiles. For this here, we fitted with 10 different Gaussians. We end up with a relatively good fit with 10 Gaussians, but based on interferometric studies, you can see these published results, there are actually many more spots. So we only sort of managed to get 10 maser profiles out of it, but interferometric data says many, many more actual maser spots. But our values in the next panels, so panels B and C is our linear polarization. B is the fraction of linear polarization. In this case, it's hovering around 5%, but it does vary quite a bit across the spectrum. The panel C is the polarization angle, so the linear polarization, what sort of angle you see it at. And again, it does vary quite dramatically from here sitting about minus 40 degrees to plus 10, drops down again, etc. Panel D is our Stokes V parameter, and this is circular polarization, and it's a measure of your right circular polarization minus your left circular polarization. Panel E is just your fractional circular polarization, so it's V over I. And the last 2 panels we calculate from V and I, and this is your right circular and left circular signal. So blue is your right circular, the dashed magenta is your left circular. And you can see over here, just at about minus 45.6, your right circular is more than your left circular. Here at about minus 44.6, your left circular is more than your right. So you do get variations in different intensities in your right and left circular. And I'll touch on this in a moment as well. Because we've looked at many masers, we've ended up and coming up with quite a few new observations. First of all, in G173, it's the first observation that's been done of circular polarization in this source. And then we had 5 sources here where it's the first detection of any polarization in those masers. So it shows you polarization studies are not generally done. So as soon as you look at polarization results, you do see a lot of things that haven't necessarily been seen before. So quite a few new observations. Then now I want to go into the sort of crux of some of the results that to me are quite powerful. This is of source G173. I've chosen it more because we have four very clear maser profiles, quite clearly separated. We fitted more Gaussians in here, but there are four major profiles. And then if you look at the polarization of each of these profiles, the linear polarization percent of this first profile sits at about 7.5. The second one only sits at about 6. And the fourth one sits at about 4. So different polarization fractions of these maser profiles. The polarization angle, the first one is sitting here at about 10 plus 10 degrees. Second one is probably 1 or 2 degrees. This third one here is about minus 22. And this fourth one is about minus 15 or so. So again, very different results for the different maser profiles. Circular polarization here in green. This first one is about plus 3.5%. Then second one, 2.5%. This very last one sitting at about 1%. So quite different. So a result, and I'm going to speak more about this again later, the polarization does differ substantially between the maser profiles in a different spectrum, on a single spectrum or single region. Then this is a result that we've spoken about a few times, or I've spoken about a few times in presentation. To me, it's a very powerful result. It's a source we've looked at on a regular basis, Monoceros 2. And in the total intensity, you can see it here. The methanol has 4 fairly prominent maser profiles. You see it here. You can see between the profiles there are differences between the linear polarization percent, a little bit between the angle. The circular polarization is actually different. It's negative here for this first large profile. The major profile here, it's positive, so it does differ. But the interesting thing is when we looked at the same source, and this is 2 months later, you see a vast difference in the polarization. It's gone from both of these up above 5% to between 2.5 and 5. The polarization angle's gone from about plus 50 to minus 50. The circular polarization is actually swapped directions, gone from negative to positive, and this one, the large profile, positive to negative. So we are seeing time variable polarization. We saw it in 1 or 2, and one of the other sources, NGC 7538, where we had multiple measurements, we see it there as well. So to me, this is quite a powerful result. The next thing we did that we looked at is Zeeman splitting and magnetic fields. So just a quick rehash in terms of what Zeeman splitting is. I think most people are very familiar with masers, that we have a higher energy level that's overpopulated and a lower energy level. And as the molecule goes to the lower energy state, photon is emitted with a very specific energy. And because of the amplifying effect, you get a very strong maser signal at a specific frequency. However, so that's if there's no magnetic field. In the case of a magnetic field, the energy level splits, and you end up with 2 different energies. So this larger energy here ends up being your right circular polarization for a positive magnetic field, and the lower energy, you only get left circular polarization. So if you look, so this sort of schematic on the right, you end up with what will be your right circular polarization, your left circular polarization at different frequencies. So you see 2 maser profiles. This is nice and separated. Sometimes they overlap substantially, but you can pick up these 2 maser profiles. If you look at the frequency difference, or a proxy for that is your velocity difference between the 2 profiles, you end up with your Zeeman splitting value. And your Zeeman splitting value, it's easy to convert that into a magnetic field. It's just a linear conversion. There's a lambda G factor which gives you the conversion. And from your Zeeman splitting, it is possible to calculate your line of sight magnetic field. So it doesn't give you your total magnetic field. It gives you the magnetic field, the line of sight magnetic field between the maser and the observer. So that's your Zeeman splitting. If we look at the I spectra, and I want to focus again on G173 just because it's got nice clear maser profiles. If you look at these panel at the bottom, that's F, you will see your right, you can just barely see a slight difference between your right and your left circular polarized signals. But if you look at it, it looks like the velocity is identical. You can't see a shift in the velocity. However, if you fit these profiles with Gaussians, that Gaussian fitting gives you a very accurate result. You can see it here. I've just got some data on the left. If you look at the velocities here, we calculate from, and this is from the Stokes I, the velocities. But for example, this velocity at 13.9, which is this second large peak, you can see we're getting 6 decimal figures of accuracy. It's incredibly accurate as soon as you fit with the Gaussians and you have a good set of data, which we do. By fitting your right and your left with Gaussians, you can actually come up with a very small velocity shift between your left and your right circular polarization spectra. The split is tiny. It ends up being less than a single channel separation, but you're able to measure it. And we've got here from this source, we published 2 Zeeman splitting values. So from the source at minus 13.9, it's at minus 13.9. The Zeeman shift is just under a meter per second shift. Given that we're measuring kilometers per second, the shift is 1 meter. So a very small effect we're picking up here. In this fourth profile at the end here, this minus 7.5 kilometer per second velocity, the Zeeman shift is 1.3 meters per second. We did get Zeeman shifts of all of these profiles, but the others have fairly large error bars, so we didn't publish them, but we get the Zeeman shift of those 2, and from that we calculate the magnetic field, and it's of the order of tens of milligauss. Yeah, so we're able to calculate magnetic fields. Interesting, we can compare magnetic fields. Some values have been published previously. This is of source G188. We got 2 magnetic fields. It's for the maser profile here, the one sitting at about 10.68 kilometers per second. The other one for a profile here, the large profile sitting at 10.88 kilometers per second. Here the Zeeman shifts and magnetic field values. We get values of minus 58, minus 32. Previously published values for the source sit at about minus 10, and that's from Fleming's 2008. So there are differences. We have quite a few views as to what could cause the difference. One being that these magnetic fields do change over time. We have some views about the method, that this cross-correlation method, because it does average results as opposed to get specific results per profile. So we have to be a bit skeptical about these average results, but no, we at least similar order of magnitude, both negative magnetic fields. So magnetic fields do compare to previous results. Then the next comparison, I'm going to go back to the source I spoke about earlier. That's this Monoceros 2, where we've got 2 different observations. You're able to get magnetic fields from all 4 of these prominent maser profiles. Just showing the one here. So from this largest profile sitting at about just on 13 kilometers per second, we get some very good statistics. And if you look at the values for this magnetic field for the 2 observations, the first one in December 23, second one February 24, the magnetic fields are actually quite different. And that difference aligns with the difference we see in the polarization. So this here is the circular polarization. You can see magnetic field going from positive to negative, very similar for the circular polarization. The linear polarization percentage here, so changes substantially between these 2 observations, as does the polarization angle. So we're seeing corresponding variations in the Zeeman splitting, which is effectively your magnetic field, the linear and circular polarization. And for our other sources where we've got more than one epoch or observation, we see similar correlations between changes in the magnetic field and the polarization. So our view is quite a powerful result, not something that has been seen before. And I'll mention a bit later, but our view is what we are seeing, and this is the conclusion we had in the paper, is that we have magnetic fields threading through the masering cloud, and these magnetic fields are change with time and change within weeks to months, and that is causing the change in the polarization that we observe. Now I'm going to move on from there. I've gone through just a summary of the results we've seen and published in the paper, just to how some of the results we've come up here challenge some of the general perceptions. Perhaps some misconceptions, but some views that the industry, people in the industry, or sort of the maser community hold, particular about polarization of masers. And without being too critical, these are two challenges we had to our paper that the reviewer brought up, and I'll explain why the reviewer came up with those comments and how we showed that that understanding is in fact not correct. I've got 3 examples, and I thought I'd show this not to try and be critical, but just to indicate that you actually have to be quite skeptical sometimes about previously published results. They're good results, but sometimes new information does actually contradict what has been seen previously. So the first one here, this is variations in polarization. I've taken this graphic from Fleming's, which, as I said, was seen as the general understanding where the magnetic fields coming around a maser, about a star-forming region measured by masers, seems to be static, and all of the magnetic fields seem to align. Based on that sort of view, it's a commonly held view, the reviewers comment about our position angle, polarization in general, is that what we see between different maser features should actually be consistent. And then if we're seeing variations, it's probably due to error in our measurement. And the idea of the review is, why don't we just publish an average value for all of the masers that we see, or the maser profiles we see in a single spectrum. So, and it's all based on having the view that the magnetic fields are constant in a star-forming region. You go back to our data says that is not the case. You see, if you look at the position angle for linear polarization, this first maser feature here, its position angle is below 50, about 48 degrees. For this large feature here, it's above 70 degrees. So we've had to go back and comment. First of all, we have, because of the way we've done our calibration, we do have very accurate results. So we've updated to kind of make this point clear and to give feedback to the reviewer. We added quite a few comments to the paper. First of all, we added a section to explain, because of that Muller matrix calibration, our polarization values are actually very accurate. Our position angle accuracy is probably better than 1 degree. Our fractional accuracy of linear and circular polarization is probably better than 0.5%. So our results are quite accurate. And then we were quite explicit in the paper to say that, if you look at a single star-forming region, the polarization can differ significantly between maser profiles. It doesn't always align. It might align in some star-forming regions, but in those that we studied, it seems to vary dramatically between the maser profiles that we observed. So that was the first sort of challenge to some of the existing understanding. The second one gets a bit technical, but I won't try and go into the detail. But quite often, in terms of published results for circular polarization of masers, you end up with something called this S curve. It's like a S put on a S let it put on its side or a sine wave curve, you end up with the shape of your V-type spectrum. And here's an example, Fleming's 2008. There's their total intensity, their I maser spectrum, nice and clean, and they show their V as this nice standardized S shape. The reviewer's view was that unless you see this S curve, your circular polarization results are not credible, are not reliable. So it does question whether our results are reliable, and the view from the reviewer is because we haven't calibrated our results correctly. So we've, if you go back to our results here, that's what sometimes people see. Our results for circular polarization look very different. And the reason why they look different is between your right circular and left circular polarization, you can have differences in intensity, and they can be substantial, and those substantial differences hide any type of S-curve that you might see. Quite often you see these sort of fairly strong circular polarization in 6.6 gigahertz OH masers because they're the separation between your left and your right circular polarization is quite big. So to try and just address this concern, we went back both through the reviewer and added detail in terms of paper, but just confirming why our Stokes V spectrum are accurate and our calibration is correct. And then just adding a section to explain that your right and left circular polarization can actually be quite different in terms of intensity. And because of that, you don't see this S-shaped curve. So quite different to what people expect based on a lot of the recent publications. Okay, and then just a final one in terms of sort of expectations. We, in our paper, published our definition for what is our fractional or our percentage circular polarization. It's just Stokes V upon Stokes I. This is in fact a conventional measure. It's not something we made up. It is the standard, what is seen as the standard. However, the reviewer's comment is we should actually use a different formula. And this formula relates to that S-shaped curve for circular polarization. And based on the reviewer, we should use it because it has become a standard in the maser polarimetry community over the last 2 decades. We did quite a bit of research to actually understand why this was being said. And then we've gone back with some fairly strong feedback. First of all, that our calculation isn't actually the correct general definition, and we actually included quite a few references stating that. We also note that the reviewer's idea of what we should have used in terms of a formula has actually been published before. We kind of checked these publications. In fact, this use of this formula seems to go back to a paper in about 2001, and incorrectly so. And if you can go back even further than that, the reason this formula exists, it is actually a measure of Zeeman splitting and not circular polarization. People have used it as a proxy and incorrectly as a proxy, but the initial derivation of this formula goes back to about a paper in 1960 that Dirk found from somebody called Galt. So to try and just be clear about this, we added an appendix to our paper where we went through the maths to show that this derivation is in fact a measure of Zeeman splitting, and is because of that, it's inappropriate to be used as circular polarization. The reviewer wasn't happy. We left it in the paper. Should have it in the paper, but we did leave it in, and we've just given quite strong feedback, not in the paper, but just to the reviewer, that in our view, it's incorrect to use it, even though it has been used and published previously. So it's interesting to see that definitions used previously, almost certain things become a norm, and because people copy it or take it from previous papers without actually having checked it in detail. And it's interesting to pick these things up. You would think that just about everything has been checked and double checked, but it's not always the case. Okay, so that sort of brings me to the end of the talk. As I said, it'd be a fairly short summary of our paper. I thought the information was interesting. So just in summary, we've had a survey looking at a range of 6.7 gigahertz methanol masers. We've made one new discovery, which is interesting. We've detected polarization of several masers for the first time. And it's interesting, we see that about 2/3 of the star-forming regions have masers. We know, and it's been published previously, that most methanol masers are time variable. So we see that again. But then, because we're looking at polarization, many of our masers are polarized to a level of a few percent. And interestingly, only cases where we don't see polarization is when the polarization ranges are below our detection limits. Now, each spectrum we come up, we're looking at single dish, so we end up with these several maser profiles all in one spectrum. So we end up in all our cases of a spectrum of all of these overlapping profiles. And now, if you want to actually analyze this in more detail, you do need interferometric observations. So you do need an array to actually get the data, to observe the data, and then from that you can define and look at the properties of individual maser spots as opposed to this general view that we have. Then some of the things I said, challenging the industry view that the polarization does vary and does vary significantly between maser profiles in the same spectrum or the same star-forming region. And that polarization can change over time. And this is a result that, to me, is quite novel and that hasn't been picked up before. From our results, we measure magnetic fields through Gaussian fitting, or we measure Zeeman splitting through Gaussian fitting of our R and L spectra and calculate the magnetic fields. And interesting, where we have more than one observation, we can see both the Zeeman splitting, which is obviously a proxy for the magnetic field, and linear and circular polarization all seem to change in a similar manner. And it's our view that what we're seeing in these maser regions is that there are magnetic fields that thread through the maser itself, and the magnetic fields change, and that causes the changes we see both in Zeeman splitting, linear and circular polarization, and explains why all of these, the polarization and the Zeeman splitting, all move in the same kind of manner or simultaneously. Okay, that brings me to the sort of end of the presentation and the summary. Thanks for the opportunity to present, and happy to answer any questions.
Oh, thank you very much, Paul, for the excellent presentation. This was awesome, and at some point it made me feel like sometimes it's very important to confront the reviewers because they might also be wrong. So thank you for sharing your experience with us. So now I'd like to open the floor for questions, and it seems like we already have one question. So Dr. Jude, can go ahead.
Thank you, Paul, for the nice presentation and clear explanations. My question is, why do we have few observation of these OH masers for periodic methanol masers to carry out polarization studies? And secondly, I missed what you said is responsible for the for the different peaks in the profile.
I'll probably let me answer that first. That second question. You wanted to know why we get multiple peaks in the profile. So
yes,
let me just get a nice. Let's go back a bit. Like this. Now this one's a nice example. So each profile here, each peak here, represents a different maser spot. And if you actually look at an image, you will see these as different maser spots in your image. But because we're looking at a single dish, we're looking at a whole region. So we see all of these maser spots in one spectrum.
Sorry, it's not actually this particular profile that I'm looking at. This is another profile. I don't know if they all mean the same thing.
Is it this one, perhaps?
No.
Tell me when you want me to stop.
Yes. Yes.
So this one is, we're seeing 4 prominent maser spots in the same profile. So if you look at the image, you will see 4 separate maser spots in the image. And it's just in terms of where they sit in terms of velocity that you get them overlapping. The fact that the one on the left the shape on the left looks like the shape on the right, that's just coincidence.
All right.
So these are just 4 maser spots. These 2 are overlapping. The 2 on the left are overlapping, and the 2 on the right are overlapping. And I think this shape, the outcome of the shape is just a coincidence. You look at, depending on how strong each of the masers are, as to what this profile will look at. This mono 2 maser, we have monitoring results over a fairly long period of time, and you'll see this one going up and this one coming down. So it does vary depending on when you look at it.
Cool.
And if you want to go back, sorry, just ask that first question again.
Okay, the first question is, why do we have few observations of hydroxy masers for periodic methanol masers to carry out polarization studies?
So my understanding, and this is just a general comment, is that most observations are done with methanol masers. So most results are methanol masers, and that's because the methanol masers are stronger and easier to observe. There are just fewer observations of hydroxyl masers. It just is the case. There are actually fewer hydroxyl masers, I think, than methanol masers. There are probably, I think, about 2,000 methanol masers. The excited OH masers, there are only about 50 of them. I'm not too sure how many in terms of the ground state OH masers there are, but they're probably less than the 2,000 methanol masers. And then in terms of periodic masers, so we haven't touched on that, but you see the intensity of some methanol masers varying in a periodic fashion. Some seem to vary in a random fashion, some are stable. But as far as I know, periodically variable masers have only been seen in methanol. They haven't been seen in OH. I hope that answers the question.
Okay. Yes, but what could be the reason for non-detection in periodic methanol masers?
Yeah, so that I can't comment on. I think we're not even sure. There are lots of views as to what caused the periodicity in methanol masers. Why we don't see periodicity in hydroxyl masers, I'm not sure. I think we still need to understand why we get periodicity in methanol masers. I think there are lots of ideas, but it hasn't been proven conclusively or thoroughly yet.
Okay. Thanks, Dr. Jude, for your questions. I hope you were answered. Dr. Willis, can go ahead.
Thanks, Francis, and thanks, Paul, for such an interesting, well-explained presentation with great results. I'm just wondering, and these are general questions, is it possible to infer the B field morphology, the morphology of the magnetic field from polarization? And if that's possible, what do you think it is? Is it helical? Is it straight, like the illustration that you showed? So something like that. I don't know if it's possible to estimate the magnetic field from polarization as well. And if possible, have you tried to verify or confirm the results from the Zeeman splitting with polarization, just to check that you're getting like the 38 milligauss that you showed? There is a page, I think page 14, you mentioned that, is it this one? I think, yes. Page 14, you mentioned that there is change in magnetic field strength with time. So what could be causing this variability in magnetic field strength? Is there a physical mechanism that could be responsible for this change? Because most of the time we have always assumed that it's constant. So it would be great to find out if they are changing and possible mechanism that is responsible. Another comment that I have is on the accuracy of your position angle. So I don't know, these are images and there could be beam effects. I don't know the kind of results they are, but why is it possible to achieve a position angle of 1 degree? In the cases of images that I studied, it's quite uncertain, the position angle. So I would be interested to find out how you achieve this very high accuracy in position angle to 1 degree. And then in page 20, about the S shape that is expected. Apart from your results, are there any other results that support non-S-shape behavior that you are seeing, the profile that you are seeing? Thank you very much, and sorry for the many questions. It's because of the interesting nature of the talk. Thank you very much.
Thanks, Wes. That first question to me is one that we've been looking at for a long time. And we've got a whole lot of results which we are keen to publish in our next, we're coming up to publish it. We almost see what we've published here as a precursor for that. We wanted out of this paper to show that you get changes in the magnetic field, or changes in the magnetic field that align with the change in polarization. To me, we wanted to get that result out of this paper. We've got on this source, and I've mentioned it in, I think, a previous presentation, on this source, we've got about 18 observations, and we show that the polarization and Zeeman splitting seem to be periodic, which we think is a very powerful result. And if it's periodic in the Zeeman splitting, that means your line of sight magnetic field is or probably rotating. And because we see the linear polarization angle also being periodic, we think the linear polarization angle is also rotating. And the only explanation we can give for that is that we have some, you mentioned it, a helical or spiraling magnetic field that is causing this behavior. We don't show it in this publication, but we hope to show it in the next publication. We're busy working on that paper at the moment. And we think the reason why we get that sort of spiraling magnetic field or helical magnetic field is because in the accretion disk, or we think, we're not sure, and I'm not too sure if this theory is sort of what we're thinking about is correct. You get a lot of turbulent disk winds in the accretion disk. And we think it seems like those winds have magnetic fields associated with them. And that is potentially a cause of why you would get these helical magnetic fields in the accretion disk that impact the maser. So that's our current thinking. As I said, it's something we want to publish soon. That's sort of our next and what we think is hopefully a really big publication. And we see this, just what we've shown here is just to almost set some of the parameters, sort of foundations for what we're going to come up in that paper. So that's our view in terms of your first question. Your second question was around why are these results accurate? We calculate the angle, that polarization or position angle is calculated as a function of your Stokes Q and Stokes V polarization products. And in calculating that calibration Euler matrix, we look at standard polarization calibrators. We look at 3C286, 3C138, which are the standard calibrators out there. And if you look at our results and you compare them as a function of frequency, or compare them to other values, or you look at the error values that come out of that calculation, it shows you that the polarization angle accuracy is less than 1%. That's the whole calculation behind the Euler matrix, actually gives you the polarization properties of your calibrator. So you don't even use them, you actually get them out of the calculation. And that's where I get that 1% accuracy of the position angle from. There could be other effects in the position angle, the atmospheric effects, ISM effects that could and possibly do impact this. That might cause differences between the different masers, but given that these are all in the same line of sight, it's unlikely that that would cause the magnitude of the differences we see here. So it's interesting also, if you look at when you see images, the way that the polarization angle is calculated in CASA and how that calibration is done is a lot less precise than what we do for the single dish. So the error in sort of the image, the polarization values in the image data is likely to be a lot less accurate than what we see in the single dish. So that's probably the best answer I can give for that second question. And sorry, your third question, I remember it, losing track here.
Oh yeah, thank you very much. Yeah, I'm satisfied with those two. And the last one was the S shape that you're talking about. Apart from your result, the S-shaped profile, if you remember it, the one that the reviewer was complaining about, the one you mentioned. Are there any other studies that are in support of your studies, or is it only yours that is not seeing the S shape?
Okay, no, that's a very good question, because you will see this S shape when your right circular and left circular polarization have the same intensity. So when you see that, you'll get this S shape. We've seen it for one of our previous paper on the excited OH circular polarization. We had a very nice example of this S shape. But as soon as you get, let me see, something like this. As soon as you get a case where you get different intensities between your left and your right circular polarization, as you do in this source here, it's nice and clear in this source, your Stokes V is the result of this difference, whereas your S shape is going to be very, very small. So you're still in the spectrum. We've actually I've played with these spectra, and if you try and artificially adjust your left and your right circular polarization spectra so they have equal intensity and do the subtraction, you come up with the S shape. So the S shape is there. It is just that it's obscured because you get this difference in R and L intensity. And you ask for other examples, you see this difference in R and L intensity, in particular in 6 gigahertz excited OH masers, because you get quite big separations in those. Sometimes you're getting 100% R or 100% L. So it's not unusual to get this difference. What I do think could be happening is, and the reviewer actually alluded to it, if you try and over-correct or calibrate your spectra. So part of the calibration is you have leakage from I to L. So if you subtract, in your calibration, subtract too much I from L, or too much of that calibration, you end up, you are artificially adjusting the intensity of R and L, and it gives you this S spectrum. So it could be the case that some of these, and it's hard to do this calibration if you're looking at image data, because people artificially try and correct for this in image data, and you can overcorrect and end up seeing the S spectrum. So I think part of this is sometimes overcorrection. We know we haven't got overcorrection or overcalibration because of the way we've done the calibration, but R and L spectra can be different intensities. Interesting, we haven't been able to find any published methanol maser results which show R and L having different intensities, which we think is interesting and was quite surprising. But you said you do see it in the 6 gigahertz excited OH spectrum. So generally, every time we've seen polarization results from all the publications we've looked at and seen polarization results from the methanol spectra, you see the S shape. Ours is the first time where we show this difference between R and L. And I think so you can understand why the reviewer actually questioned our results. You kind of understand where the reviewer was coming from. It was a valid criticism which we had to defend.
Thank you very much, Paul.
Yes, Prof. James, you can go ahead then, Raul. Prof, are you there? Okay, Raul, you can ask in the meantime while we get Prof back.
Hi, Dr. Fallon. I enjoyed your presentation and I was looking up your paper. I have a general question. Can the orientation of the magnetic field with respect to the line of sight influence the polarization variations?
The simple answer is yes, because you can have a magnetic field that is not aligned with the line of sight. So you are only looking at the component of that magnetic field that you see in terms of the line of sight, if that makes sense.
Yes.
So if you take your line of, if you know what that angle is, if you know that angle, you can take your magnetic field, you measure it, divide it by cos of that angle, and you'll get the total magnetic field value. But let me just go back to a spectrum where we've got, try and see which one would be useful, where we've got magnetic fields. Yes, this is probably just good to have a look at this. So we've measured the line of sight magnetic field, which is up to say 58 milligauss. The actual magnetic field is going to be bigger than that because you're only looking at a component, you're looking at a lower limit. So your magnetic field is always going to be larger than this. Now, the fact we've got linear polarization here, so panels B and C show that we've got linear polarization, means there's a component. So we're looking at the line of sight magnetic field here that we calculate. But because we've got linear polarization, it means that there's a component of the magnetic field in the plane of the sky. But at this stage, there is no clear way to calculate the component of the size of the magnetic field that is in the plane of the sky. We know it's there from the linear polarization, but we can't from our linear polarization calculate its components. So we know there's a component in the plane of the sky and there's a component in the line of sight that we can measure. And the question that was asked earlier about if we are able to show that there's a helical magnetic field, we can actually calculate its parameters. And from that, we could calculate the total magnetic field. But we're hoping to see if we can do that in our next paper.
Okay. And my last question is, if the magnetic field is perpendicular to the line of sight, which polarization state would be the most dominant, which would be the highest in terms of polarization state from the Stokes parameters?
Okay, so if you see it in if it's perpendicular to the line of sight, it's going to be in the plane of the sky. Okay, which means you're going to get no component in the line of sight, so your Stokes V, these spectra in green, would be 0, and you would see strong linear polarization because that is due to your magnetic field that's in the plane of the sky. Hopefully that makes sense.
Sir.
Can I ask now?
Yes, Prof, you can go ahead.
Okay. Thanks, Paul, for the presentation. Very, very good. Always good to see polarization result, which is what Deck, yourself, of course, myself, advocating for more in observation for full Stokes. The results you see in the Mesa polarization, have you at any point tried to compare it with what we see in polarization in, say, dust emission or line emission, maybe for sources that has been published before? Do you see any agreement in the two results, maybe in the polarization direction or the strength of the magnetic field?
I think that's a great question. I've looked very briefly at some, and it's probably something I haven't done enough of. What I would expect is, because you're seeing this change in direction, what you see in terms of the dust is those magnetic field observations tend to be fairly static. So I would expect that these two be different.
Yeah.
I haven't checked order of magnitude, but it's I think a very good point. Something we should check and compare.
Yeah, because there has been a few measurements in line emission. I would suspect that the polarization measurement in dust and mesas could be different, because you're seeing it from different, probably different angles, right? Because the dust might be somewhere else, then the emission from mesas will be excited at a different point. But if you look at polarization, for example, molecular lines, thermal molecular lines, do we still see something consistent with what you see in mesas?
It's a good point. Something that's worth checking. And no, we haven't looked at any of those publications for these sources in detail and tried to do a comparison. But yeah, it's a good idea.
Oh, cool. All right. Thanks again, Paul.
Okay, any other question? If not, I think we can close the meeting. And once again, thank you very much, Paul, for taking your time to present to us your work, and see you all next week.
Yeah, thanks for listening all, and yeah, have a good afternoon.
Thank you very much. Likewise. Bye-bye.
Thanks, everyone. Cheers. Bye-bye.